So when you look at a medical X-ray, you expect precision.
Right, absolutely.
Like you want to see a clean, jagged white line that shows exactly where the bone broke.
Yeah, the diagnosis is totally binary at that point.
Exactly. It's broken or it's not.
Yeah.
But, for the last couple of years, deploying artificial intelligence in a serious enterprise environment has felt, well, kind of like looking at a broken X-ray machine.
That's a really good way to put it.
Right? Because you feed it this complex data problem, you type out your prompt, you just get an answer back, but it's this blurry black box.
Yeah, you don't know the exact mechanical path it took to generate that answer.
Right, and you can't always reproduce it across different sessions. And if you're a professional who's actually relying on that output to drive business intelligence, I mean, that lack of deterministic precision is just a massive liability.
Which is exactly why the transition from, casual conversational prompting to rigorous engineered AI workflows is probably the most critical hurdle in data science right now.
Yeah, for sure.
Because the stakes in a corporate environment demand that X-ray level of clarity. I mean, we are moving way past the era of treating large language models like magic 8-balls.
Oh, totally.
We really need to start treating them like highly configurable compiler engines.
And so today, we are going to fix the machine. We're doing a deep dive into a real-world, high-priority industrial capstone project. It's called FeatureBot.
Yeah, FeatureBot.
It's basically a system designed to build an AI-guided workflow for predicting income levels. And we are cross-referencing this specific architecture with Google's official published best practices for AI prompting.
Right, because the goal here isn't just to talk about theory.
Exactly. Whether you are, a senior data scientist managing production models or maybe a project manager trying to operationalize AI, we are going to reveal the exact mechanics of building a reproducible, high ROI workflow.
We're mapping that gap between generic chat and advanced data science.
Right. But to map that gap effectively, we kind of have to start at the foundational layer, right? Like how instructions are even parsed by these models.
Yeah, because if the base communication protocol is flawed, the entire automated loop that you build on top of it will eventually suffer from, drift or just catastrophic hallucination.
So looking at Google's prompting best practices guide, they codify this very specific architecture for instruction design using an acronym, PTCF.
Persona, task, context, and format.
Right, and the guide offers this pretty straightforward baseline example, which is just writing a tagline for a washing machine.
Which sounds simple enough.
Yeah, but a generic prompt is just write a tagline for this washing machine. But when you apply the PTCF framework, it becomes highly structured.
Right, you build it out piece by piece.
Exactly. So the persona becomes you are a seasoned advertising writer. The task is create a concise tagline. The context is the machine gets clothes extra clean, it has 25 customizable settings, and fits in a small space.
And then the format layer.
Right. The format is use an active voice and be no more than 6 words.
Now, on the surface, defining a persona sounds like, I don't know, a psychological trick, like we're just role-playing with the system.
Yeah, like improv or something.
Exactly. But we really need to look at what is actually happening mathematically within the model's architecture. Large language models are fundamentally massive probabilistic engines.
Right.
They are predicting the next token in a sequence by calculating probabilities across a high-dimensional vector space based entirely on their training data.
And that training data contains essentially, the entire spectrum of human text. Everything from highly technical documentation to, like, poorly written Reddit arguments.
Precisely. So when you submit an unconstrained prompt, the model's attention mechanism is pulling probability weights from all of those disparate latent spaces at once.
It's just too broad.
Yeah. But by explicitly declaring a persona, like seasoned advertising writer, you are actively pruning the probability tree.
You're narrowing it down.
You are mathematically constraining the model to sample only from the neighborhood of its neural network that actually corresponds to professional marketing copy. You're filtering out the noise before the generation even begins.
Wow. And we actually have this masterclass example of this exact constraint in our source stack today. It's a system prompt designed for an industry solutions architect. And it takes this PTCF framework to just an absolute extreme.
Oh, it really does.
Let's break down the mechanics of it. The persona is declared immediately. It says, you are a principal solutions architect and profitability strategist.
Very specific.
Yeah. And then it says, you do not possess feelings, you do not apologize, and you do not use conversational filler. Your sole function is to process industry problem statements and architect highly specific, technically viable, and financially optimized solutions.
Notice the negative constraints there. You do not possess feelings. You do not apologize.
Right, it's so cold.
It is, but by instructing the model to avoid conversational filler, you're doing two things. You are saving token bandwidth, and you're reducing the chance of the model drifting into the helpful but subservient customer service persona.
Which is kind of the default fine-tuning for most commercial models, right?
Exactly. It wants to be your friendly assistant. You have to explicitly tell it not to be.
And the prompt then enforces what it calls tone and linguistic constraints, which basically acts as the format layer. It strictly bans specific vocabulary.
The banned words list is fascinating.
It's crazy. It tells the AI, you are strictly forbidden from using the following words. And it lists things like, well, words like tapestry, intricate, pivotal, vibrant, crucial, testament, underscore.
Yeah.
It also bans bloated phrasing. Like you can't say, it is important to note, or use the phrase serves as, when the word is will suffice.
That specific list of banned words is incredibly revealing about how these models work. Words like tapestry and underscore are statistically overrepresented in the reinforcement learning from human feedback, the RLHF phase of many foundational models.
Really? So they're like crutch words for the AI?
Basically, yeah. They are linguistic tells. By banning them, the prompt forces the model out of its default, slightly academic, kind of generic output style.
It strips away the fluff.
Exactly. It forces it to synthesize actual, unadorned technical prose. It requires the model to work harder on the substantive logic rather than just, relying on high probability transitional filler.
And it goes even further into the task and context layers with an anti-hallucination protocol.
Oh, that part is critical.
Yeah, it explicitly states zero speculation, do not invent case studies. If a metric is highly variable, state the driving variables rather than hallucinating a static number.
Which grounds the AI in reality.
And for the output structure, it actually mandates a rigid 4-part format. It requires root cause mechanics, then ranked solutions with exact execution paths, then implementation constraints focusing on the single highest probability point of failure, and finally, a binary go-no-go decision matrix.
When you structure a prompt with that level of architectural rigor, the output ceases to be a novelty.
Right.
You aren't getting a generated essay anymore. You are getting a deterministic, actionable data object that you can actually pass down an operational pipeline.
Which kind of brings us directly to Google's 3 C's of prompting, right? Be concise, be clear, and be consistent.
Yeah, the 3 C's.
But at first glance, demanding that a prompt be concise seems to completely contradict the massive detailed constraints of that solutions architect prompt we just reviewed. I mean, that thing was huge.
It does seem contradictory, but the friction there really comes from a misunderstanding of what concise actually means in the context of machine learning inference.
Okay, what does it mean then?
Conciseness here does not mean brevity. It doesn't mean short. It means high information density.
Ah, I see.
An optimal prompt strips away all the pleasantries, all the implicit assumptions, all the ambiguous modifiers. It leaves only the exact parameters required for execution. So yes, the solutions architect prompt is long, but its information density is near perfect. There are no wasted tokens.
Okay, that makes sense. It's like giving directions.
Yeah.
If you're giving directions to a master chef, you can just say, make a deconstructed apple pie, and they'll know what to do.
Right, they have the context.
But if you're giving directions to a teenager who's never cooked before, you have to be way more specific. You have to say, you are the cook today. That's your persona. Make dessert, that's the task. The apples are in the fridge, there's your context. And give it to me on a plate, not in a bowl, which is the format.
That is a perfect analogy. The LLM is the teenager in this scenario.
Yeah. And then clarity and consistency, they tie directly into how the model manages its context window. The guide explicitly warns against swapping vocabulary midway through an interaction.
Yes, consistency is paramount.
Like if you define a data structure as a matrix in your initial prompt, you cannot refer to it as a spreadsheet or a table 3 turns later.
Exactly. And the reason for that is mechanical. The context window operates using a key value cache, the KV cache.
The KV cache, what exactly is that doing?
As the conversation progresses, the model stores the mathematical representations of all previous tokens to maintain state. It's how it remembers what you were talking about. If you introduce a synonymous but mathematically distinct token, like using the word spreadsheet, after you've already established matrix, the model's attention heads have to split their focus.
Because it treats them as two different concepts.
Exactly. It might map the new term to a completely different set of assumptions, which effectively fractures the logical continuity of the task. So semantic consistency isn't just about good writing, it is a strict requirement for maintaining the integrity of the KV cache.
Wow. Okay, so understanding that foundational layer, how to lock down the probability distribution, maintain state within the KV cache, that is what allows us to actually deploy this technology against a hard engineering problem.
Right, moving from theory to practice.
So let's transition to the client problem that the FutureBot project was built to solve. We're looking at project code FBFE 2025 Q3.
Catchy name.
Very corporate. It was initiated by a business intelligence and analytics team, and they were basically trying to iterate faster on tabular machine learning workflows.
And the core friction this client is experiencing is deeply familiar to anyone working in data science today.
Yeah.
They explicitly state that their traditional manual feature engineering process is slow, it's inconsistent, and it's incredibly difficult to audit for fairness. They essentially need a systematic, AI-guided process to replace the ad hoc intuition of individual data scientists.
Because feature engineering really remains the most labor-intensive bottleneck in the whole pipeline, doesn't it?
Oh, absolutely, by far.
We have these incredibly sophisticated algorithms now, XGBoost, Light GBM, deep neural networks. But when you're dealing with tabular business data, you can't just feed raw database tables into the math. The algorithms require numeric signals.
Right. Tabular data is notoriously stubborn compared to unstructured data like text or images.
How so?
Well, with a photograph, a convolutional neural network can automatically learn the features, right? The edges, the textures, the shapes. It extracts them itself.
Because it's just pixel values.
Exactly. But with a customer database that contains birth dates, categorical job titles, skewed financial metrics, the models rely heavily on the human data scientist to explicitly transform that raw data into predictive signals.
It's like prepping ingredients for a massive banquet, right?
That's a great way to think about it.
The algorithm is the oven. But if you put whole, unpeeled onions into the oven, the meal is completely ruined. Feature engineering is the chopping, the marinating, the pairing of the ingredients before you bake it.
Yes, precisely. For instance, if you have a column for transaction timestamp, the raw Unix epoch code is totally useless to a linear model. But if you engineer a new feature that calculates the rolling 7-day average transaction volume, you suddenly provide the model with a highly predictive behavioral signal.
And so for this project, the client is actually using the famous UCI adult income data set to test the FeatureBot architecture.
Which is a classic data set.
Yeah, it's roughly 48,000 rows of census-style data. And the target variable is binary classification. They are trying to predict whether an individual earns less than or equal to $50,000 or greater than $50,000 annually based entirely on their demographic and employment attributes.
And it serves as an excellent proving ground because it perfectly mirrors the messy, imperfect reality of enterprise data.
It's not clean at all.
No, the source documentation outlines several structural quirks that the FeatureBot system has to navigate right out of the gate.
So let's examine the missingness matrix first. The document notes that missing values are not cleanly encoded as nulls or nans like you would hope. They're actually populated with a question mark string.
Which is a huge trap. If an automated pipeline misses that string encoding, the downstream algorithms will interpret the question mark as a distinct, valid category.
Wait, really? It won't just ignore it?
No, it assumes it's data. For instance, if the occupation column has question marks, the model might learn to associate the question mark itself with a certain income level, rather than understanding that the data is simply missing.
Oh, wow.
Yeah, you have to handle missingness structurally. You have to identify whether the data is missing completely at random, missing at random, or missing not at random, because the immutation strategy you choose drastically alters the model's predictive landscape.
And then there's the challenge of severe class imbalance in this data set. Only about 24% of the data set actually falls into the greater than $50 K category.
Class imbalance is a nightmare because it warps the gradient descent process during model training.
How does that happen?
Well, if a model simply predicts the majority class, meaning it just guesses under $50 for every single row, it achieves a baseline accuracy of 76% without actually learning any underlying patterns at all.
Because it's just playing the odds.
Exactly. The loss function isn't sufficiently penalized for missing the minority class. This forces the engineering team to move away from raw accuracy and optimize for metrics like the F1 score or the area under the precision recall curve. Those metrics provide a much harsher, more realistic assessment of how well the model identifies that critical 24%.
Okay, and the dataset also contains these heavily skewed numeric variables, specifically capital gain and this census weighting metric called FNLWGT. With capital gains, the vast majority of the population registers a zero, right? Which creates this massive spike at the origin of the distribution, and then it's trailed by a really long, sparse tail of high-value outliers.
And linear models struggle immensely with high variance, long-tail distributions like that.
Because of the outliers.
Right. The outliers exert disproportionate leverage on the regression coefficients. They pull the decision boundary way off center. So dealing with that skew requires log transformations or targeted binning just to normalize the variance.
And critically, the data set includes protected sensitive attributes. We're talking about sex, race, and marital status. The presence of these variables introduces the requirement for fairness diagnostics, which we will analyze heavily when we look at phase 4 of the project later on.
Yeah, that's a massive component.
But before FeatureBot generates a single line of code, the architecture requires a baseline. The engineering team deployed a standard logistic regression model utilizing one-hot encoding for the categorical variables and standard scaling for the numeric features.
Establishing that baseline is crucial. It is the only way to mathematically quantify the ROI of the AI intervention.
You need a starting line.
Exactly. Logistic regression is a highly interpretable linear algorithm. It does not natively understand complex interactions between variables, which actually makes it the perfect blank canvas to measure the impact of engineered features.
And the one-hot encoding.
That just binarizes the categorical columns. It turns a marital status column into distinct columns for married yes and married no, with ones and ohs.
Got it.
And the standard scaler just normalizes the numerical ranges so that a variable like age, which ranges from 18 to 90, doesn't mathematically overpower a variable like education num, which only ranges from 1 to 16.
Okay, so once that baseline is locked in, the team initiates phase 2, which they call the 4-step loop. This is really the core operational engine of FeatureBot. It consists of context, AI propose, implement, and evaluate.
And the methodology here is extremely rigorous. Step 1, context, involves feeding the LLM the dataset schema, the results of the exploratory data analysis, and that specific missingness matrix we just discussed.
Right. And then step 2 is AI propose. This requires the model to generate feature ideas, articulate the mathematical rationale behind them, and actually write the execution logic in Panda's pseudocode.
Then step 3, implement, shifts the execution back to the human operator. The human integrates the generated code into a Colab notebook, which is just a cloud-based Python environment, while actively auditing it for data leakage.
And finally, step 4 is evaluate, where they test the new features using cross-validation and log the deltas in model performance.
Looking closely at step 2, we can see the direct application of Google's constraint principles in action. The documentation details prompt template A, which initiates the whole cycle.
Let me read template A. It says, given schema plus EDA context, propose 5 transformations with rationale, leakage risk, and Panda's pseudocode. Optimize for F1 on greater than 50K.
The precision of that instruction is fantastic. It forces the model to bypass general brainstorming entirely and output a structured operational blueprint.
Yeah.
No fluff.
None. It constrains the output volume to exactly 5 transformations. It sets a specific optimization target, the F1 score in the minority class, and it mandates the inclusion of a leakage risk assessment.
And the specific features the AI generated in response to template A actually demonstrate a deep mechanical understanding of the tabular data challenges.
They really do.
One of the proposed features was capital gain 0, which is just a simple binary flag indicating whether capital gains were greater than 0. And the AI's documented rationale for this was that it handles sparsity, flags non-zero gains.
Which directly addresses that long-tail skew we discussed earlier.
Instead of forcing the logistic regression to calculate a coefficient for the entire wildly varying range of capital gains, the AI just simplifies the signal. It tells the model, just look at whether they have investments or not.
Binary, yes or no.
Exactly. It transforms a noisy continuous variable into a sharp, highly predictive binary signal. The Pandas code for this is incredibly straightforward. You're essentially mapping a Boolean to an integer, but its impact on a linear decision boundary is massive.
The system also proposed a feature called AgeBin, with the rationale that it captures nonlinearity for linear models.
This is a great one. The relationship between age and income is inherently nonlinear. It resembles an inverted U shape.
Because your income goes up and then down.
Right. Income generally rises through your 30s and 40s, it peaks in your 50s, and then it declines post-retirement. A standard logistic regression attempts to fit a single straight line through that curve, which inevitably results in massive error margins at the extremes.
So what does the binning do?
By instructing the pandas code to utilize a function to discretize the continuous age variable into deciles, or specific categorical bins, the AI effectively allows the linear model to assign independent weights to each distinct life stage.
Oh, that's clever.
It bridges the gap between the simplicity of linear regression and the complex reality of human earning curves.
Beyond just transformations, the AI actually generated interaction terms, too. It proposed multiplying the age variable by the education num variable, and the rationale provided was that this interaction serves as a seniority or skill proxy.
Interaction terms are where feature engineering actively synthesizes new information. Think about it. A 25-year-old with a high education number is just starting their career, so their income might be moderate.
Right.
A 55-year-old with a low education number might have plateaued a long time ago. But by multiplying the two variables together, the model creates a compound vector. A high resulting integer strongly correlates with a highly educated individual who has also been in the workforce for decades.
Which is a powerful proxy for specialized senior management roles.
Exactly, which are heavily concentrated in the over $50 K bracket.
But, the brilliance of Template A isn't just in the feature generation. It's the mandatory inclusion of that leakage risk assessment.
Data leakage is the silent, catastrophic failure mode of machine learning.
What exactly is it, for the listener who might not be in the weeds of ML?
Data leakage occurs when information from outside the training dataset specifically, information about the target variable, accidentally bleeds into the model during the training phase.
How would that happen?
Well, say an AI suggests a highly complex pandas transformation that involves calculating the mean income for a specific zip code and applying that to the features. If you execute that calculation across the entire dataset before splitting your data into training and testing sets, you have leaked the answer key.
Because the testing data was included in that mean calculation.
Exactly. The model will look like an absolute genius during validation because it has already peaked at the target variables of the testing data. But the moment it hits production with truly unseen data, the performance will just plummet.
So by forcing the AI to explicitly document the leakage risk for every proposed feature, the prompt shifts the burden of validation. It requires the LLM to analyze its own pseudocode and flag operations that rely on global aggregations or forward-looking time series data.
And the human operator acts as the final firewall in Step 3 and Step 4. The evaluation isn't just based on a simple train test split. The architecture mandates stratified 6-0-20-20 splits, fixed seeds, train-only fitting.
Stratified K-fold cross-validation.
Yes, which is the gold standard for robust evaluation, particularly when you have class imbalance. It partitions the dataset into multiple subsets, or folds, ensuring that the 24% minority class ratio is perfectly maintained across every single fold.
And then it trains on them iteratively.
Right. The model is trained on a combination of folds and validated on the holdout fold, and this process is rotated. If the AI's proposed agement feature boosts the F1 score in fold 1, but causes the performance to crash in fold 4, the feature is rejected for instability.
It has to be consistent.
It must demonstrate a consistent, measurable positive delta, an improvement of 3 to 5 points across all splits to actually be accepted into the final registry.
Wait, I have to push back a little here, though. If the AI is writing the code and it's suggesting the features, aren't we just blindly trusting a black box? How does the human not get entirely replaced here?
That's a very common concern, but the dynamic here actually requires a fundamental shift in how we view human-computer interaction.
Okay.
The AI is operating as an autonomous hypothesis generator. It writes the code and assesses the initial risk. But the human data scientist has transitioned from manually writing the pandas transformations to managing the execution environment.
So you're orchestrating the pipeline.
Exactly. You are orchestrating the K-fold pipeline, you're reviewing the delta metrics, and you're enforcing the architectural integrity of the system. You are the lab director. When the AI proposes a transformation, you execute the ablation study to determine its true mathematical value.
Okay, that makes sense. So the project moves into phase 3 when the initial cycle kind of hits a plateau, and Google's prompting guidelines have a dedicated section on iteration, emphasizing that the initial output is really just a baseline.
Right, if the results stall, you have to break the task down and add sharper constraints.
The FeatureBot workflow, Phase 3, is titled Cycle 2 and Ablations. They retire template A and they deploy prompt template B, which reads, given validation errors, suggest 3 interactions to reduce false negatives, provide code and fairness notes.
Template B demonstrates a highly advanced diagnostic approach.
Because it's targeting false negatives specifically.
Yes. The human operator has analyzed the confusion matrix from cycle 1 and identified a specific structural failure. The model's overall accuracy might be acceptable, but the recall metric is suffering because of a high rate of false negatives.
And in this classification context, a false negative means the model evaluates an individual who legitimately earns over $50,000, but the algorithm incorrectly classifies them into the lower bracket.
Exactly. And the business implications of a false negative depend entirely on the deployment environment. If this model is utilized for targeted marketing of premium financial products, a false negative represents immediate lost revenue. The algorithm just bypassed a highly qualified lead.
Oh, wow. Yeah.
Conversely, if it's used for a credit risk assessment, a false positive approving a high-risk individual might be way more dangerous. But here, the lab director has determined that capturing the elusive minority class is the absolute priority, so they constrain the LLM to exclusively target that specific quadrant of the confusion matrix.
By demanding exactly 3 interactions designed to reduce false negatives, the prompt forces the AI to analyze the specific attributes of the misclassified data points.
Yeah.
Like, it might recognize that individuals with high capital gains but lower formal education are consistently slipping through the cracks of the baseline model.
And that prompts an interaction term specifically designed to flag that demographic anomaly.
And Phase 3 also mandates those ablation studies you mentioned earlier to ensure the model remains efficient. Because as you stack multiple AI-generated features into the pipeline, you risk multicollinearity, right?
Right, multicollinearity. That's where features are highly correlated with each other, so they're just adding computational overhead without providing any new predictive signal.
So how does an ablation study fix that?
An ablation study systematically removes individual features or groups of features from the active pipeline. You literally drop the age bin feature, retrain the model from scratch, and observe the delta in the F1 score.
So if dropping the feature causes the F1 score to drop, the feature is providing unique value. But if the score remains static, or even improves without it, the feature was just dead weight.
Exactly. Ablations are the pruning mechanism. They prevent the feature space from bloating into an unmanageable overfit mess.
To execute Cycle 2 effectively, the Google Guide introduces this critical technical warning regarding the context window. It mandates, use new chats for new topics.
This is so important.
If you transition from the general optimization of template A to the hyper-specific false negative targeting of template B within the exact same session, the AI's output will degrade. Why is that?
It goes back to the mechanics of the KV cache we discussed. When you maintain a single prolonged session, the attention heads of the transformer model are forced to calculate probabilities across every single token previously generated in that chat.
Right.
So the weights of the rejected hypotheses from template A are still actively influencing the generation of the template B response. The model suffers from context contamination.
It's anchored to the past.
It is. It will attempt to recycle its previous logic, basically trying to forcibly adapt a rejected general feature into a solution for false negatives instead of starting fresh.
It's like working on a cluttered workbench, right? If you ask a carpenter to build a chair, but the bench is still completely covered in blueprints for a table, they're going to get confused. Sweeping the workbench clean by initiating a fresh session clears the KV cache.
That's a great analogy. You feed it only the schema, the specific confusion matrix errors, and template B. The mathematical probability distribution is entirely reset, which allows the model to generate novel, unanchored hypotheses.
Mastering the life cycle of the context window, knowing precisely when to accumulate context and when to purge it. That's really what separates a casual prompt user from an engineer.
Absolutely.
Okay, as we move into segment 5 of the source documentation, the evaluation criteria kind of shifts from raw predictive power to the mechanics of demographic fairness.
This is a critical pivot.
Phase 4 of the FeatureBot project is explicitly dedicated to fairness diagnostics and mitigation. Google's evaluation mandate states that AI output must be audited for accuracy, relevancy, consistency, and bias, explicitly warning that models will replicate the inherent imbalances of their training data.
And in the context of tabular machine learning on this UCI adult dataset, The bias is deeply embedded in the historical census data itself.
Because it's from the 90s, right?
Yes. The dataset contains the sensitive attributes of sex, race, and marital status. When the human operator runs the subgroup metrics on the optimized model from phase 3, the disparity becomes mathematically visible immediately.
The document logs the subgroup performance. For males, the model achieves an F1 score of 0.85 and an AUC, which is the area under the receiver operating characteristic curve of 0.92. But for females, the F1 score drops to 0.83 and the AUC falls to 0.91. So the regression is measurably less effective at accurately classifying the income of females.
The underlying mechanics of this disparity usually stem from base rate differences in the training data. Historically, the proportion of females earning over $50 in that specific census snapshot is significantly lower than males.
Right.
The algorithm is optimizing for a global loss function. It seeks the path of least mathematical resistance to maximize overall accuracy. If it finds a highly predictive signal that works exceptionally well for the majority demographic, it will heavily weight that feature, even if it degrades the precision for the minority subgroup.
So wait, the immediate instinct would be to just drop the sex and race columns from the dataset entirely before training, wouldn't it?
Dropping the explicit columns is standard practice, but in high-dimensional space, it rarely solves the structural problem.
Why not? The data isn't there anymore.
Because of proxies. If the AI has engineered complex interaction terms, perhaps combining specific occupations with hours worked and education them, those compound features often act as highly accurate proxy variables for the sensitive attributes you just dropped.
Oh, wow.
The model literally learns to reconstruct the sex or race variable based on the correlation structure of the remaining data. It effectively bypasses your restriction entirely.
That is wild. But the acceptance criteria for Phase 4 doesn't actually demand that the mathematical disparity be reduced to zero, which is often statistically impossible without just destroying the model's overall utility. It mandates a fairness report, including subgroup metrics, and at least one mitigation attempt with documented trade-offs, so it requires the friction to be surfaced and measured.
To execute this, the team deploys prompt template C. The human feeds the LLM the disparate subgroup metrics and prompts. Given subgroup metrics, propose mitigations minimizing overall F1 loss. Include steps.
The AI is not being asked to magically clean the data. It is being asked to propose procedural mitigation strategies in Pandas code. The document lists the strategies it suggests, excluding specific high-risk proxy variables, applying constraints to feature influence, or adjusting the probability thresholds per subgroup.
Adjusting the probability threshold is a fascinating mechanical intervention.
How does that work?
The output of a logistic regression isn't a strict binary 1 or 0. It's actually a probability curve, a sigmoid function ranging from 0 to 1. By default, the decision boundary is set right in the middle at 0.5.
Okay.
So if the model calculates a 0.51 probability, it classifies the individual as over $50. If the fairness diagnostics reveal that the model is consistently underpredicting a specific subgroup, the human operator can manually shift the decision boundary for that demographic down to, say, 0.45.
Oh, I see. This shifts the mechanics of the classification. You are essentially demanding less mathematical evidence from the model to classify a female into the higher income bracket, attempting to counterbalance the historical weight of the training data.
Exactly. But threshold shifting introduces a strict mathematical trade-off on the precision recall curve. By lowering the threshold to capture more true positives, thereby reducing the false negatives for that subgroup, you inevitably increase the rate of false positives. You will misclassify some individuals who actually make under $50.
But wait, we are using an AI which we know can hallucinate and has its own inherent training biases to suggest mitigations for bias in our data model. Isn't that like asking a fox to install the henhouse security system?
It sounds like it, yes. But remember, the AI only proposes the steps. Template C asks for the code and the strategy, but the human lab director must execute it in the Colab notebook, calculate the exact shift in the global F1 score versus the subgroup F1 score, and formally document the trade-off.
The final architectural decision rests entirely on human validation.
Right. The framework forces the opaque reality of algorithmic bias into a transparent, quantifiable metric that stakeholders can actually review and debate.
Okay, so having navigated the data leakage risks, the ablation studies, and the fairness diagnostics, the final challenge is operationalizing this whole workflow so it doesn't just evaporate when the Colab instance shuts down. Phase 5 is finalization and handover.
The critical phase.
The deliverables mandate an experiment log, a final report, and most crucially, The feature registry.
The feature registry is the unsung hero here. It is
Right.
the mechanism that transitions this AI interaction from a transient chat history into a permanent, valuable corporate asset.
What's actually in it?
It is documented as a structured CSV file tracking the feature name, the Python definition, the upstream dependencies, the audited leakage risk, and the specific delta AUC and delta F1 generated by that feature.
Tracking the delta AUC is vital. The area under the ROC curve gives the engineering team a single aggregate measure of how well the model distinguishes between the two income classes across all possible classification thresholds.
Hmm?
By logging exactly how much a specific feature shifted that curve, you map the exact ROI of the AI's hypothesis.
And it builds a localized knowledge graph for the entire organization.
Right.
If a new data scientist is tasked with building a churn prediction model 6 months later, they don't have to start from scratch. They query the feature registry, review the transformations that yielded the highest delta AUC on demographic data, and pull that pre-validated logic directly into their pipeline.
This directly mirrors the final recommendation in the Google Prompting Guide. Save your best prompts in a prompt library. A prompt library acts as version control for human-computer interaction.
It really does.
Once you have painstakingly engineered template B to reliably generate pandas code for false negative reduction without hallucinating, you lock that prompt down. You parameterize it, you store it in the library, and you deploy it across the team.
It creates an internal CI/CD pipeline, continuous integration, and continuous deployment for prompt engineering. The document even outlines an SLA, a service-level agreement, guaranteeing turnaround times, like 1 to 2 days for routine analytical questions, 2 to 3 days for bug fixes.
So the AI workflow is no longer just an experiment. It is a supported, scalable software product.
Exactly.
The architecture we have unpacked today, defining strict PTCF personas, utilizing Panda pseudocode to force mechanical reasoning, sweeping the KV cache clean between cycles, and enforcing rigorous K-full validation, it provides a universal blueprint.
It really is universal.
You don't have to be working with the UCI census dataset to apply this. If you are architecting logistics solutions, optimizing cloud infrastructure, or modeling financial risk, you can deploy your own feature belt loop. You define the mathematical baseline, heavily constrain the LLM's probability distribution, and most importantly, you transition your role from a passive prompter to a rigorous lab director validating the output.
You extract the conversational novelty out of the system entirely, and you replace it with engineered predictability.
It fundamentally reshapes the architecture of discovery. I mean, think about it. In the FeatureBot framework, the large language model acts as the tireless, creative hypothesis generator analyzing the EDA, finding the nonlinear age curves, and synthesizing complex interaction terms. And the human operator acts as the strict procedural referee, managing the cross-validation splits, auditing for proxy bias, and calibrating the evaluation metrics.
It's a total paradigm shift.
We spent the last few decades assuming machines would do the quiet procedural math while humans provided the creative intuition. But as we look at the reality of advanced enterprise workflows, that dynamic is entirely inverted. If AI is now the ideas guy, and you're just the referee checking its work in a Colab notebook, what happens to human intuition in the next decade of discovery? Thank you for joining us for this deep dive. Open up your environments, lock down your constraints, and start building your prompt loops today.